Good morning. Give me a moment. Ooh. Okay. I'll quickly write the agenda because I missed that. So the bitrate bad? I have no idea. That's normal, right? It seems fine. I don't know. Oh shit. Yeah, just give me a moment. I'm just gonna be writing. But so I promised I would go nowhere near those things. No, I would go nowhere near denotational semantics. I think I wrote. Yeah. Yeah. To transpile, that's how you spell that, right? Transpile to other programs, to other programs. Sample export comes to C or Yeah, like typical example. Not every. Typical examples. Not every optimization is going to be a bracket rewrite, right? Up to AC commutativity. That is line graph. No, LLVM passes. LLVM passes. What's it called? Reassociate. That is. Yeah. Okay. So the previous stream. Okay, so actually performs the rewriting and yeah, with proof. Okay. So okay, I'm gonna push this up as well. Great. Okay. All right. I guess we'll start. So, it's probably Christmas for everyone. It was Christmas for me yesterday. So, yeah, Merry Christmas. But I guess this is more important. So, actual forms of rewriting proof. So, right now, a lot happened between now and last stream. So last stream, I was fucking around, doing not really much of interest. Um, it was mostly me just realizing that, let's say, it was mostly me realizing that for me to get proof automation for Hero, work on a better proof automation framework. If I wanted to get proof automation working, I would need to do a lot better than what we have, like what we had before, right? Here's the proof optimize. This is the proof automation that I had, right? It was like this tactic called opt. How it would work is you would just write opt, and then it would just opt the program. So for example, if you had a lemma, if you had like a theorem, right? Test, right? If you had a theorem that basically proved x rewrites to y, you tagged it with opt. You tagged it with opt. You have to put opt ideal. If you tagged it like this, if you were inside a proof of something, so like prove theorem prove this, and then you had x rewrites to y, you just call opt. You just call opt, and then it'll use this. It'll use previously defined theorems. Anything tagged with opt ideal, it'll put it into an array, and then go through every single one, and just try to apply it. This is like the level of proof automation that I had. The thing is that like this is nice, it works. Just the big issue is that the tactics, they're like really annoying to use, and they're locked into lean. They're like locked into lean. So for example, I added the ability to add these things called opt procs. So it's kind of like sim procs, if you know what that is for the simp tactic. So you would go like opt proc, name, and then it would just literally just do like if you would do you would do this, right? You do like if, so you get like an expression. I'm pretty sure it's like on x. You would get an expression. It'd be like, so let x let match. I don't know, like, how does it look like? X looks like LHS plus 0, return none if it doesn't match, and then like return, you would return two things. You return the optimized version with a proof. So proof add 0 rewrite. Yeah, add 0. So you would return a proof. So basically how it would work is you would define these things called opt procs. You would get a lean expression. So this would really be lean.expr would be a lean expression. And then you just like match on it, and then you return a tuple where it's basically the new thing, and a proof that LHS plus 0 rewrites to LHS. This would be this thing. Returns a proof. Now the thing is that it would be wrong to say that this isn't scalable, because it scales for the entirety of simp, like the simp tactic. But it would be, the thing is that these things aren't optimizations. This is like a tactic. This isn't a thing that you can. This isn't a thing that you can. For example, right? You can treat this as an optimization. Okay, anything in X rewrites to anything in Y. This is an optimization. You can export these, right? You could literally like export this into JSON and like put it on the internet, and like people can use this optimization. People can't use this. There's no way to turn this into something that people can use. This works on the lean AST, and it has all of these like it's basically like a lean meta program. Like, how could you put a lean meta program? How could you share that around? That's not an optimization. This is like a cheating. It's like a fake thing. It's not optimization. It's like these things you can share around, but this is a lean meta program. This is not what you want. This is not what you want. So I guess the idea of what I want to do at the moment, because I realize that this just doesn't make sense for what I'm trying to do. So the alternative to that is, for example, if I had a def name, this takes in a IR. Yeah, this takes in an IR, and then returns IR. So this is basically this thing, and then you would match like LHS plus 0, return LHS, else return the thing back, right? So this is an optimization that basically matches on the IR. If it's LHS plus 0, returns the LHS. If it's something else, just return it as is, and this will hold by like reflexivity, because this rewrites to this, and 0 rewrite LHS. These are like the two proofs. So like you could do a theorem where you go like theorem. You could do a theorem like this. So basically we have IR, which is an AST, which is more like the like abstract representation of the syntax, and then you have like your expr. So I'll show you an example of the IR. It's like a super duper simple example, right? This is like a super simple IR. It basically takes in this is a nat. This basically takes in the type. The way of representing this is a bit like unorthodox, but like really, for example, if I wanted to like create this expression LHS plus 0, it would really just be add IR dot var 0, and then like IR dot const 0. Just IDX. Just make that like 0. All right. So here is my AST at the moment. Here's my AST. This is IR add 0, add IR const 0. This is basically like a concrete expression. And then, for example, if you were to do IR.eval, the above thing, right? This would give you a function. This will give you a function that has the semantics of this. So for example, like this will give you this, right? If I put 10 in, 20 in or something, it'll give me 20. So IREval turns this like AST thing into semantics. So how it works is you get some expression, there's a Lean expression. You do something called denoting. So, oh wait, not denoting. You need reify. So you do expr, you reify, and this turns it into an IR, which is this concrete AST thing. So we're going from this is like a meta program. So this would convert any old expression, right? For example, these expressions here, right? It'll turn this expression, right? It'll turn this expression into the like concrete like IR thing, into the concrete IR AST. So you do something called reification. So there's reify, and reify returns a proof that ir.eval is actually equal to the same semantics of that expression. So this is reify. So then we have an IR that is when we evaluate it, it gives us back this expression. And then we want to do something called denoting. Denoting is the reverse operation. So you want to denote IR. This gives you an expr, and then returns a proof that expr, yeah, it's just ir.eval equals expr. Like the proof is just like connecting them together. So so you take a Lean expression, like this expression, right? You reify it. So this turns your expr. This is a meta program. So it works on a Lean expr, the expression. Turns it into IR, which is really just like an inductive type like this, right? It's just like this. It's just like an AST, like your program representation. And then the reverse operation is you need to denote that. So you can take this IR, turn it back into an expression, and then that's the reverse operation. So it returns a proof that IR eval equals expr, IR eval equals expr. So for example, like if you had LHS, let's say like you begin with LHS, you want to reify that into an IR. You want to opt the IR, so you get a new IR, you optimize it, and then you want to denote this IR to become RHS, right? Then you want to return RHS, and a proof that LHS goes to RHS. So how do we actually so for example, this RHS, this is like super easy because it's literally just like a function. It's a function from IR to IR. It's a function from IR to IR. So this is the easy part. This is the super duper easy part. But how do we actually recover some sort of proofs from this? How do we recover some sort of proofs? So IR reifies to LHS. So we get to from this reify function, we get a proof. So what does this proof say? This proof says if we evaluate the IR, this is actually equal to the same semantics as LHS. Okay, what does optimization give us? So opt is a function that sends IRs to IRs. So we'll just like copy this up here, right? This optimization has something called a well-formedness on it, right? So you can implement this optimization, but let's prove it correct. So the theorem statement is really ir.eval. So okay, so it's for all IRs, ir.eval IR rewrites to ir.eval name IR. So this is basically saying for all IRs, if you were to evaluate that IR, what is that? That's just the expression, right? Because This comes IR comes about by reification. So this is you basically for all IRs, the semantics of that IR rewrites to the semantics of that evaluated optimized IR, right? Optimized IR. So okay, we know this from opt well formed. Opt well formed says that ir.eval IR rewrites to ir.eval IR tag, right? This is opt well formed. Okay, so we have this proof. We get this. So the reification turns our expression into an IR. From this IR, we can optimize it. We know that this is true, right? Because of opt well formed, this IR rewrites to the optimized IR. And then when we denote, we have IR dot from denoting, we have IR.eval IR tac equals RHS. So we have these three proofs. So we have these three proofs. We have LHS. So we have LHS equals IR.eval IR. Okay, what happens here? Well, we know that IR, this rewrites to IR eval IR tac. Oh wait, but this is just equal to RHS. So by transitivity, we can chain these proofs. So this goes to this. Oh wait, but this rewrites to this. But this is actually equal to that. So by transitivity, we basically have LHS rewrites to RHS. That's it. That's it. So this took me a long time to figure out. I've never touched a concrete semantics like textbook. I haven't done anything. This is like I'm like really new to this. Like my experience has literally been just banging my head against the wall. Looking at this is like the only maybe I can find maybe I can find the original blog. But yeah, this is like a post by Timothy Mao. No, I don't know. I don't even know this guy. But this is the only thing I could find on this kind of proof step, right? So like this entire thing, this is called denotational semantics. I think this is called denotational semantics. So the idea basically comes down to two things, right? You reify your expressions to bring these things into the IR concrete world, and then you denote to bring things back down. These are like denotational semantics. So I believe denotational semantics, you have, so denotational semantics works on like this, right? So this is your denote operator. So you have statements, and this turns it into like math, semantics. So basically, you have your concrete IR. This thing, this weird bracket thing, is called denoting. You turn this IR into your semantics, so the denoting operator. So, for example, if I have my IR, I'm going to the semantics of this IR rewrites to the semantics of the optimized IR. That's denotational semantics. This entire thing here is like denotational semantics. So, yeah, this is what I'm going to be doing. So, like this like I know I've said here, right? To go further, this is unrealizable denotational semantics. For this, right? This is necessary for being able to export my rewrite rules, because not every rewrite rule is a dumb rewrite LHS to RHS, right? Not every rewrite rule is a dumb X to Y. Rewrite rules, for example, if I wanted to implement something like this, right? LLVM's reassociation pass, right? This reassociates commutative expressions in an order, in a specific order, right? So it puts all of the indeterminates on one side and all of the constants on this side, and then changes all the orders of things. That's like something you can't do with a simple like pattern match. Like you can't do this. Like let's say you made a theorem and it was just like this to this. You can't do that with these like super simple theorems. So you need to implement programs that transform IR to IR. But if you implemented it using like Lean's metaprogramming thing, that's a metaprogram. That's not something you can just give to people. It's like hooked into the Lean like ecosystem. So basically, you need denotational semantics to get these IR things, and you need to like implement a program that sends IR to IR, and then you prove that program correct for all IR. The semantics of that IR rewrites that IR. I mean, this is literally equivalent to the denotational semantics stuff. So it's just like IR rewrites to opt IR. Like this is basically this thing. So I believe this is denotational semantics. Right? I haven't taken a single course in this. I I really wish I did. The thing is that up until now I didn't realize how necessary it was. If I realized in the past how necessary denotational semantics would be, I would be I would have known this by now. But I'm glad that we're able to do this on stream at least. So I think I've been mucking around here testing. Yeah. This is an example I wrote to myself as well. This example where like you reify, you do the things, you get the well-formedness proof, you denote, and then you chain these. This example I wrote on my own, and this is the example we came up with a couple seconds ago. So I'll just leave these here. So, denotational semantics is important. For this, it makes sense to do this. I think like maybe we can go on like Wikipedia. The thing is like I'm probably bastardizing this entire like everything to do with this, which is my fault. Uh, oh well. Maybe I can find a better like PDF. I swear that was a good PDF. That was a good PDF. That was a good PDF here. Who's this? Oh, Spider. Hey. It's good to see you. It's been a while, huh? Yeah, it's been a while. Yeah. How have you been? All right, here. So he's like denotational semantics, right? So you're going from the concrete like IR world into the semantic world by using this operator. This is basically my like IR eval. This operator. So we go into the program world, into the semantic world, the math world. So So using so this is so evaluate this plus this is actually just plus and evaluate the inside expressions. So like you can unwrap things. Yeah. So denotational semantics is gonna be it's gonna be really annoying, but I'm gonna have to implement it. So this is what I'll be doing this stream, and hopefully this will be hopefully a bit comprehensible. I think. Yeah. So right now I have reification. What's that? Oh, you've been busy with uni. Oh yeah, same. It's been a year for me as well. Oh well. Yeah, it's been going well. So remember there are two operations. Reify. This sends an expression to an IR. There's another this is the inverse of reify. This takes an IR to expression. And you would really hope that reify denote IR is just denote expr is actually equal to expr. Like you would hope this is true. It is true. So the denote procedure and reify procedure, they need to return the IR and a proof that it's actually equal to the IR, and then it returns an expr and a proof that it's equal to IR. So like given if these are implemented correctly with the correct like proof stuff, if you compose them together, you can just prove that they're equal. So that's the thing. So right now, I have a reify IR expression. This takes in a body, and just converts this body into an IR. So at the moment, this doesn't prove anything, which is a shame. It doesn't prove anything at the moment. I'm gonna move this at the bottom. So right now, here is what I have. So currently, I have this thing. This is basically an expression. This is like I use this like weird for example, this. I just put anything in here and then like close the bracket up. So if you put anything in here and you have this and this, this will just hook into this procedure here, which just like accepts these expressions, and then like tries to optimize them. This is like my debug. This is like my debug. So I put this in at the moment. So in here, let's actually print out what reify actually does. So yeah, this is annoying. So yeah, this is my reify. So let's just log log at. Yeah. Please let me print this. Log message. Bruh. How do I log? Oh, it's log info. Okay. There you go. All right. So yeah. So if the actual like reified like expression, I think we can see it. Okay. So let's just like hide all this crap. Okay, so this is the reified expression. So we have x plus no sign wrap x. What does this turn into? This just turns into add no sign wrap that. Like that's to be expected. This is to be expected. So I think we just need to go on from that and return a proof because I don't return a proof at the moment. So yeah. So I need to return a proof. Not denoting. Well, I mean, I guess this is denoting. Sort of. Yeah, okay. So, yeah. So I need to return a proof. I need to return a proof because at the moment, right, this IR, x plus x, this just returns the expression. It has no proof. And that's necessary. That's necessary because remember our steps. You want to reify, you get a proof, optimize, denote, and then you get a proof. Then you chain them together. Transitivity, LHS goes to this rewrites to this, RHS, chain them together, LHS rewrites to LHS. That's what we want. That's what we want. So, yeah, that's the goal. So hopefully we can figure that out. Okay, so I think I might need a monad here to do this nicely. Because I'm looking at, so BV decide. BV decide is a tactic in Lean that takes any expression in terms of bit vectors and booleans and then converts this into a SAT expression and feeds it into a SAT solver and then proves the goal. This uses denotational semantics entirely. For example, here, this is the denote symbol. This is like, I think this is like the main thing of this entire tactic. It's basically saying denoting the Boolean expression is actually equal to the Boolean expression, like evaluating it over the assignment. Oh, this is basically saying, okay, the denoted expression, like in the Lean world, is equal to the denoted expression of the SAT expression, the Boolean SAT expression. Anyway, this code is basically where I'm like looking at for inspiration. Yeah. So I think yeah, reify. Where is it? .of. Okay, so here's where the reification happens. So yeah, I'm gonna need to like do some monad shit. Hopefully I'll remember. I'm trying to think for a sec, because yeah, this is not useful. No. Okay, so this is like cache. Okay. I think I might move things out of a single file. This might get like annoying. Maybe. Yeah, I'll move things out of a single file. All right, so I'll do it this way. Yeah, just take everything. Is this necessary? Okay. Yeah, it's necessary. Okay, it's the IR, and this is the rules. These are optimisations. Okay, so yeah, so I guess I haven't showed how optimisations actually look like. This is what they look like. So there are two different things. So optimisations, they have. I know how I showed optimisations like this, right? So the well-formedness would be for all IRs. You basically want to show that the IR eval, use eval the IR. This rewrites to eval opt IR. That's it, right? The thing is that this is not for all IR. This is for all IR, and for all IRs, right? And then also for all assignments. And then for all width. So this is like for all v sigma. Okay, so what does this even say? This is basically saying this assignment. So this is for all IRs, right? For all IRs, but this assignment means so for all assignments of variables. So for example, if you have an IR var which is 0, for all assignments will basically mean an assignment sigma is basically a map from a nat to IR INN, where n is something to be determined as well. So every expression in IR var has an IR IDX So example, this is an expression, but IR is parameterized by some IDX. This IDX is not bit width. So previously, right, you would have IN32, but IR32 is not 32 bits. It's the 30. It's the 30. It's the 33rd. It's the 33rd bit width variable. So this would be IR0, but you have Z0 is actually equal to 32. This would be like a separate thing. So we have these two things. So this is a nat that goes to nat. This is basically variable index goes to value. And this is basically bit goes to bit width. So you compose these together. So for example, if we look at this, right, this is a variable. This is the variable 0. This is of type IR IDX. IDX is the IDX index into the bit width variable. So if we were to actually do IR eval on this, given the width assignment and the actual assignment, this would actually become the expression sigma 0 sigma 0 of type Z, G, whatever. I don't know. I don't even know how to say it. Psi. Is it psi? Yeah, IDX. That's it. So this would be the expressions term. This would be the expressions term. So yeah, that's just how it works. So it's for all IRs, for all assignments, and then for all width assignments. So like that's just how it worked out for me. What the hell? Hello. Yeah. This is how it worked out for me. Usually with these, you would only use one environment. The thing is, this is for width. This is for width assignments as well. So for example, if you wanted to have a rewrite where it's like n m, and then you want to rewrite some variable, like it's like polymorphic on two kinds of bit widths. So like you would have a bit width variable. Yeah, it's enchantment table language. Yeah, this has been the hardest thing to wrap my head around. I only came up with like this idea to use like two different environments when you evaluate something like yesterday, and like I said before, like I don't know anything about denotational semantics, but I'm learning. Hopefully this is right. So yeah, so the well-formedness predicate, the well-formedness proof is not for all IRs, IR, eval, IR, rewrites to IR, eval, optimized IR. It's not for all IRs. It's for all IRs, for all assignments of those IRs, and then for all bit widths of those assignments. That's how it works. So this is the well-formedness predicate. So it's for all width assignments, given those width assignments are valid. So like if you wanted to specify a rewrite over this bit width and this bit width, given that n must be less than that bit width, this allows you to specify that. So for all width assignments, for all valid width assignments as well, for all assignments of variables, and then given any IR, given any IR, and this is saying the right hand side, like the left hand side rewrites to the left hand side rewrites to the right hand side. That's it. This is super simple. So expressing that, yeah, expressing that is expressed here. It's expressed here. But yeah, so I just need to do the proofs like correctly. Oh yeah, here's an example of like this rule. So add 0, x plus bitvex 0 rewrites to x, of course. There's any width assignment, like this works for all bit vectors, for all like bit widths. And then what else? Oh, the implementation. This is a function. This is a function that takes IRs to IRs, right? IR maps to IR is a function. So this IR will basically match on add. IRCon 0 returns LHS. For anything else, it just returns it. The proof of correctness is super duper simple. It's just this split. There's two different cases. This case is just reflexivity, but this case needs something harder, so you just add 0. So when you get to here, it's just like, okay, how do I prove this? It's just like apply, just apply it. So that's the proof. That's the proof. So like this is a self-contained optimization that's just like a function, which is way better than the meta program. Way better than the meta program, because meta programs fucking suck. But this is a function, which is nice. So alright, I'm gonna copy out the rest of the stuff. So yeah. I'm gonna just leave this here. So, alright, this is just basic, and then like reify. It's like the big one, right? No, this one's the big one. Okay. All right, so let's get a proof working. Let's get a proof working. So this should really return. It also returns a proof that yeah. So that's what we want. We want a proof. So let's just use some monad shit. Let me just think for a bit. How does BV decide do it? It's just basically the most important question. How's it do it? We'll just do an example. So. Mhm. Okay, so eval expr, which is basically the thing that we care about. Proof that, yeah, eval equals that or none if it holds by RFL. Okay. Yeah, so this is just recursive. This just turns into the thing that you care about. Yeah, so change the proof. So given a proof that given a proof that this is a thing. Yeah, what's the proof? Find your congruence proof. Just evals and atoms. And then just chain them. Congruence theorem. You just chain them, right? I don't know. But I think this is a good start. I think this is a good start. So I think we might just we'll just take a look at this thing. The width is not. Yes, how it works is it takes in. This is a bit width index. Yeah. It's just XP. And then this is a proof that this is like the proof that it's equal. I don't think we'll use this M. Use a track bit variables. We'll see. Traverse the context. So this needs a bit of context. Because this is like a context. This is like a contextual thing. So we need to do monad. So and then this is the evals at. It's just like proof. Eval reify state. This is like important. So this is the proof that what is this called? How is this constructed? How is go bit vector literal. Yeah, so this is evals at atoms is proof. So okay. Reified version. Yeah, so okay, atoms, where the atoms is the assignment stored in this monad. So, okay, yeah. So this is what we want. So atoms assignment. This is the thing that we care about. Yes. Okay. So, yeah. So, when we reify the expression, we really want to construct the proof, which means we need to know the assignments, the sigma ahead of time. We need to know this ahead of time. But we construct it here, so we should have it beforehand. So yeah. So we should have it beforehand. So the atoms assignment. Yeah. So this creates it on the fly with a cache. So it doesn't like do extra work. Because these are supposed to be huge expressions. But the thing is like I just calculate everything in the beginning because these are supposed to be functions. So for example, these are so when what the reify does, this is supposed to take in functions of the kind like this, right? It's supposed to take in this. It's supposed to take in any list of bit vector variables, right? Any list of free variables, then return something. And these things are in terms of the bit vector variables. Yeah, so like I know everything ahead of time. This makes things easier for me. So I can literally just construct the assignments automatically. That's nice. So yeah. So atoms assignment. Yeah, so these are things that I have automatically. So what should I do to like create a new M? And then yeah, we want to create a new thing where we have this assignment of these. Takes in the assignment, and then this takes in this takes in a list. This takes in the assignment, right? And then also takes in. Then it also takes in the bit vectors. This thing. So this comes is a width assignment. This is what is it? How do you pronounce this? How do you pronounce this? Psi? Surely this is psi. KS. What? X. Oh, come on. Because. How do you pronounce this shit? Xi. Psi. Xi. 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 Okay. Psi. Xi. Psi. Psi. Alright. Yeah, so we already have this. We've already created it after the fact, but we need it now to construct the proof. So, yeah. We need it now. Assignments. This is really so it's the width assignment such that all assignments x var id idx this idx into okay is an index into width assignment. So let's do this. We'll just like copy this code. So yup. Let's copy this code. And then we want to have that these are non-zero as well. That's like an annoying thing. Just give me a moment. These are non-zero. What's the problem? Yeah. Good. What else? Beta. What's the problem? Okay. Oh, there's a meta M. Yeah. Meta M state. Okay, that works. So this is supposed to be this. Return great. So yeah, so Adam's assignment. We have our assignment already. So that's good. Okay, and then we want to mk eval expression. Right. Reify state. this takes in an index, which is thing. Eval. This is the expression. This is the IR2Expr. This is like this is an expression of I. Actually, we can make this nicely typed. This is Q IDX. Right? Is that nice? Can I do that? Yeah. And this returns a M. So it's like this. Ooh. Okay, what's the problem? Oh, that makes sense. Okay, and then literally just return eval to expert. Yup. IDX, and then we want Adam's assignment. This is, yeah, Adam's assignment. So, okay, ir.eval, what does it take in? What does it take in? Okay, ir.eval takes in the width assignment, so that comes first. Yeah, that's the width assignment. So that's Q. Yeah, so this is we need to get really just get the state, which is our okay, reify state st dot q that. Let's tell them to do. Okay, implicit argument idx. Yeah, give me a moment. St dot that. And the IR. Okay. Better. This is a term. That's not helpful. Yeah, this is just an expression. Okay. So we have okay. So I guess we'll start from the beginning. We'll start from the beginning, which is basically we'll start with here, this bit vec. Maybe there's like a variable. There's like a free variable. So this is bit vector literal. Of net, this, shift right. Return none. This is what, yeah, this is the thing. So register E is an atom of width. Yeah. So this is that's the thing. That's one of the things. Okay, so this is a reified. Perfect expression. Yeah. Okay. So this should return a reified IR, which takes in just an reified IR, which takes in this. Yep. Great. So this will put errors everywhere, but that's fine. Should we do? Okay. How about we give a try with the poison literal? So we basically want to return this tuple of this thing. So the original expression was the expression itself, and then the proof that IR eval is equal to the original expression. So like we'll just give it this go. So theorem, what do they call it? Poison. So for all is basically saying IR eval, IR const poison. For all assignments as well. Just for all assignments as well. Yeah. This is the like these are like the ones. What's this BV expression? Yeah, it's perfect. So okay, eval var. So eval of all assignments. So we need assignments as well. So this just takes in like assignments. Yeah, so okay, I guess we'll like do this. So this is sigma this, so psi sigma const poison, it's just equal to poison, but of width Z. Okay. Oh. Okay, and what's this one? This is an IN. What's this one? Okay, this should make sense. This should make sense. So, yup. The proof of this is just like super duper simple. Pretty sure. Simp. Easy. Yes, IR eval. Yeah, I mean this I think this might hold definitionally, even. Yep. Yeah. I wonder what they need to prove this. What's the problem with this? Oh, I guess it doesn't hold definitionally because it's like if statements and stuff. Fair enough. Oh, well, the rest of these hold definitionally. That's nice. Okay. Well, this holds definition. So, yeah, we're basically constructing this proof. Yeah, so for all width assignments, eval that poison equals poison. Which makes sense. Yeah. Yeah, alright. So we need to do this. So what's the proof of this? This with oh yeah, we need to get st q q get And then just pass these. What's the IDX? Yeah. What's left? Yup. What's left? The proof that IRExpr to expr. This is like the expr. This is the IR. Oh, come on. How do I get to expr? But like it's the Q. Anyway, have This is yeah, that makes sense, right? This is the quoted version of that. Yep. Why is this in this namespace? Perfect. What am I missing? That's it, right? Am I missing anything? No. What does this take in? This thing, this thing, this thing. Oh, that's everything. Const eval poison. What's poison? Well, we can only hope that that's right. So this is body. Expression. Oh, I guess we don't need this. It's just IR. Body. Proof. Proof. So the proof is just this. Okay, what's wrong with this? Why? Why? Oh. I guess like, pure. Yep. Okay. I think that's right. For one of them at least. We'll like give this a try. Give this a try. Is there a way, is there like, eval? Can I just like, meta m? What's the problem? Okay, well, at least I can run this. Okay, let's give this a try. So let's, what's this expression in? Actually, no. Running this here doesn't make sense. We'll have to run it from basic. We'll make a elaborator that lets us test at least. We'll just copy this. What is the inverse operate? What should we make denote? Denote brings things down. I guess we'll like try with this thing to bring things up. So lab term. I think removing all of this is the right idea. Then turning this into something like this. Right. Reify state. Okay. And then we'll call this. Oh, you need to be within this you need to be within this context for it to make sense. Uh could not synthesize for in notation. Oh. Okay. This is not a thing. Yeah, and then just literally like return. Fine. Was it assignment first? And then we need the proofs. So the proofs. This is by exact decidable, not of. What are the proofs that I use? Of not H. Okay. What's this thing? Okay. It's supposed to be T. All right. F bars body. This is the expression. Let IRExpr. State. This is state. And then we need to actually run the this is environment. We need to actually run the expression stuff. Really, this should be called config. reifyIRExpr. That's great. Thanks for that. reifyIRExpr. Since this is I guess this should be a reader key. What is state? What? Oh, read. Yeah. Should be a reader T. Okay, this is the environment, and then we basically want to run. We want to run reify, right? m.run. How are these defined? What is this? How is run defined on that? This thing. This is an expression. This takes an environment as well. Oh, that makes sense. I guess I don't need this. I can just call it. So I can just call reify. Oh, this returns to me an index. Okay, so this is the what I'm losing is this result index. Why is it not telling me that that's a useful thing to keep? Return this. This is maybe that doesn't make sense to keep here. Maybe it makes sense to do it like this. Maybe it makes sense to do this. This is a pair. So this is you want to return two things. So let env this. You want to return the pair of results from the environment. Come on, man. What's the problem? Oh, that's going better. 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 Okay. Yep. So then we want the environment, and then we want the result IDX, right? Basically, environment dot c she psi yes. Really, this is the body has type this. Oh, come on. What? What's the problem with this? Unexpected token. What are you talking about? Okay. It's non-inductive type. What? How do you pattern match? Come on, there's an example, right? Products. Surely there's like an example of product types. Ordered pairs. Oh, shit. Shit. Yeah, that's how you write them. What's the problem? Oops. I keep bringing the key off on my keyboard. So it's this. Okay. What's this? Oh, over a binder. Okay, that's the whole problem. It's fucking. Oh, Lean has the worst error messages. Oh my fucking god. Type inference ruins everything. Alright. Yep. Yep. Alright, it's reifyIRExpr. Takes in the index. The doesn't take in any assignments anymore. Just takes in the body though. Yes. This is just IR. And then this is, we want to run this using the environment. And this is a meta M computation, so that. And then we just want to do nothing. We just want to like return, T. But then we just want to print this stuff. So we want log info. Oh, come on, doesn't it have a wrapper? What's the problem? M-expert. Okay, I just don't want to include that. Okay, whatever. Okay, well then this I can just like deriving. Why can't I derive this? Oh, because it doesn't exist. Alright, I can just do wrapper. Alright, let's give it a go. Let's give it a go. Let's give it a go. What's the problem? Oh yeah, of course. That's bullet expression. So then let's do poison. What's the problem? Unbound, not previous free variable in that. Okay. Well, this well, yeah, because it's not really yeah. Is that better? Expected type description. How about this? Okay, what's it saying? IR is just const poison. Okay. So we did something. Something happened. So yeah. So we've reified it. It would be nice to print out the expression. What's it called? The proof. Dot this is the original expression. We want the proof, though. We want the proof. We want to print the proof. Okay. Well, to get this is really we want to run this using the environment, and then we want to get that. Oh, surely there's like a nice, pretty print. Nice. Okay. What's the proof of this? The proof of this is leave that IR eval. IR const poison equals poison. What's this? This is a get 0. And if you get 0 from the leaf, this is n, right? You get 0 from if you get 0, this is n. And what is this n? N is this. So this makes sense. This makes sense. So the proof is basically saying if you eval, so this is psi. This is psi. These are the bit width assignments. This is sigma. This is the assignments. So this is the width assignments. This is psi. This is sigma. Sigma is basically just saying the 0th variable is x. This psi is basically saying the 0th bit width is n. This is returning a IR const poison, which is which has type the 0th bit width, which is just the 0. Like, so this is just n, returns poison, which is just the 0th bit width 0, which is just n. Yeah, which is just n. So this is good. We're getting somewhere. So that's good. I'm making some progress. Which is not bad. It's good. Just give me a bit. Okay. Time to get back into it. All right. Okay. So this is right. So it returns the reified expression, which is this thing, right? This thing. And it returned a proof as well. And this proof is correct. This proof is correct. Yeah. Give me a second. Let me think. Yeah, this proof's correct because these bitvecs, like this will I think this is definitionally equal to this. Let's give it a, let me just check real quick. Theorem T. This is like we have like n. N is a gnat. Okay. Um. What's this like branch? How does it like how does it like implement? To the left. Okay, so we just do like let me just like test this out. See how far I can just like branch. Um so this gets reduced as well. Okay, so I guess that's fine. I mean how far yeah, I guess that's like okay. Yeah, it gets reduced correctly. Like if I put 0 in here, this is not true because it's obviously in the wrong one. Yeah, okay, great. So our array works. Okay, so this is the correct proof. Great. We'll do variable next. We'll do variables next. So this is like super simple. Um, uh, this is probably just as easy. So, reflect poison equals poison. So I have ID. ID is equal to sigma get ID. What's wrong with this? It says type packed in. Ah, true. Yeah. So okay. So this is like there's like some wacky semantics here. So if you actually evaluate a variable, there are some issues. So when you get from an assignment, it returns a packed in. Packed in is basically the actual like bit width paired with the thing. So for example, when you do like psi get idx, it might not equal the bit width. It always does equal the bit width. But remember, like what I said before about a couple of streams ago about junk definitions. This is a junk definition because we're defining the semantics when it doesn't hold, because we don't want to prove we don't want to prove that it holds. This is gonna like proving this is always true is a pain in the ass because I gotta bring a proof with me that says that this assignment respects this assignment. I gotta bring a proof with me, which like I don't want to do that. So this is the junk semantics that we're semanticing. This is junk definition. So I wonder how they do that because I know they do junk definitions as well. I know they do that, right? Eval literal. Eval something. Eval atom or something. Eval var. Yeah, so. Yeah, I guess this is the thing for it. eval assignment. Yeah, this is like the proof that the denoting actually works. Yeah. Let me think. Let me like take a look at this. Assignment to AIG assignment. Go. Oh, this is proving the correctness of Go, which is just bit blasting. The yeah, it's just bit blasting the BV. Yeah, it's just bit blasting the expression. Yeah. Yeah, so this has got nothing to do with what I'm doing. So, like the eval is the closer one. So I guess this is just like a the one. Let me think. I guess here is not the right place. It's probably better to look at the reify. So go does something. Go or atom. Yeah, this is the thing. This is the place. So if it can't do this, it's obviously an atom, so it needs something. So yeah, MK atom. This turns a reifyIRExpr. So proof that the thing is the thing. So this proof always holds definitionally. Why? Why is it? Like, would this hold definitionally? Maybe. Maybe. We'll like give this a try. So this is var IDX. This is the bit. Yeah, so this is actually var ID. Nothing to do with indices. So how do I find the assignment? It would be nice to go from. It would be nice to go from. Variable ID to assignment. So var ID to. Because this thing's going from var ID to in something. It would be nice to go from var ID to effa into var ID. This is like the inverse. So this would be like sigma map, which is really just like a stud hash map. It's a hash map from effa to a nat. So like this is just this. So I mean, I guess like it would be nice to make it a hash map. So this is just like Sigma map. Really just like assignment to hash to map to hash set to set from of list of array of array. Oh wow, it's like it's the exact same type thing. That was easy. As so hash map FRID nat. What's the problem? Oh, this is at the end. Great. So this goes from FVARID to VARID, and this is VARID to the thing. So this is an expr, and we don't care about this. But this is what we want. We want to get FVARID. Great. And better. Okay. We just want to return an IR var ID. We want to also return the body, which is really just the body. And then we also return a proof. So they say that this proof holds definitionally. I don't know. I don't know if I believe that. Well, I don't know if this might hold. QRFL. Well, we need to actually construct the proof. I mean, this might hold definitionally. Maybe, we'll copy what they do. We'll just assume that it holds definitionally. By RFL if none. So we'll just return like none. What's the problem with that? Pure. Pure none. Okay, reflect poison. And then what about this one? This proof is not available. Why? What are you talking about? It's just supposed to be none, right? Okay, that's true. I guess not. I guess not available means none. Okay. So, what's the proof that these are definitionally equivalent? I guess we can just try. Proof. Proof. I guess Hmm. We can we could test this. How about we give this a test? So This is an expression. This is an expression in terms of, this is the IDX, this is results, IDX. Result IDX, this is taking in an IR in terms of this. So this is really have IRExpr, which is really just a queue. IR results, which is just that. Is that right? What happened? Okay. Oh, two expert. Great. Okay, expert. This. And then this is a term. This is the term of an expression. But is this definitionally equal to the body? So this is the eval_expr, which is just like an expression. It's just this. What's wrong with this? Why is it like, why is it bugging out? Why is lean like just bugging the fuck out? Let's type M. Really? Oh, true. I guess maybe it'll help to do things like this. It might be better to actually define this then. So def m.run. What does m.run take in? M.run takes in m alpha, and then makes it a meta m. But it also needs the environment. This is just .run_env. Failed to show termination. You're kidding. Oh, because I'm calling itself. Okay. Yeah, that's fine. Yeah, that's fine. So then these are always in the right place. Great. I love monads. Okay, and then so we have IR eval thing, and we want to show that it equals body. So have expr, which is really just ex equal dot com. No, we just mk equal expr. Yeah, so two expressions. We want eval expr, and then we want the body. We want to print. All right. So we've, okay. Yes, is this, okay, eval this. So is this true? Definitionally. Is this true? Is this true? So this type checks, of course, hopefully. Okay, this type checks. Let's check, is this definitionally equal? Is definitionally equal. Okay. Is there like assert? You mean like assert? Right. Is definitionally equal. Eval, expert, and the body. So this is only for this case. I don't think it is. What? Arrow and printing message unknown goal. Okay. Well, I guess assert is like too big of a thing. So just like if. Okay, so it's not definitionally equal. Oh, that's a pain in the ass. Why? Why is that? Why is that so? Why is it failing? So just doing this doesn't make it definitionally equal. That's a problem. So is this definitionally equal to x? This is the right type, of course. Like if you type check, this is the right type. Is there a way to definitionally equal but like more? Mm. I don't really know much about metaprogramming. Why don't we just like print? Obviously, this is something that is just fucking huge. But what is the type of this? This is the type of this. It's not really reducing the type. I guess this is. I guess this is definition. This is definitionally equal to n. Um. I guess this is not very useful. I don't know what to do. Well, obviously I'm looking at the wrong thing. Good one. Yeah. With reducible end instances. Okay, there's like this thing that I looked up. What about this? Okay, it didn't print yes. Of course it didn't print yes, because it's not. There's just nothing I could do. With it was like with transparency something. Come on. All. Okay, it doesn't print yes. Okay, is there a way to just like prove that like y is just not definitionally equal? Like we'll like okay, let's pin this, right? We'll pin this, and then we will write a theorem and just like check ourselves. So this is n, this is x, I and n. Tests. And this theorem statements basically saying IR eval this. Sorry. Okay, so what's wrong with this? This is IDX. This is IDX of 0. Okay. Why is this not definitionally equal? So, let's see. Okay, RFL. Why? Why? Conv RHS. Simping this like doesn't simp anything. The types are definitionally equal, otherwise it wouldn't type check, of course. This is true by just like simping. Yeah, this is true by like simping that. But yeah, I mean it's not definitionally true because it's just not. Because when you get the thing, it has to get. I'll just take a look more about I'll take a look what else they have here. This is a BVExpr var. This is an ident nat. This is the index. This is the index. Okay, sure. That's the index. Maybe the thing's more complicated because this is an index into the Adams assignment. Where's eval? Eval. This is an R array, right? As an array. Yeah, so the assignments get, if this is definitionally, like, it'll just, like, run that. Is eval more complicated than this? It's not. It's not that much more complicated. How is this this is like, I'm just like copying this. How is this definitionally true? I am copying them. So why is this, like, this should, like, be the thing. What if I change this to n? Is this true by fl? No, it's not. Why is this not true? Hmm. Yeah, give me a moment. Hello, I'm back. So, yeah. Let's see if we can fix this. The thing is like, this is very obviously not definitionally equal. It's just not. Why would this be definitionally equal? But the thing is like, why do they think? Why does BV decide say that this is definitionally equal though? Like what if I like moved it to this side, right? This is not definitionally equal, but like for them, I really have no idea why it's definitionally equal for them. Maybe we make the left-hand side something messed up, like this. This is, the sigma is this. Pack dot truncate. Pack dot truncate returns I think the issue is pack dot truncate is defined weirdly. I think. Maybe. I mean, wait, how was this? This is just get. Isn't this? Isn't this, what we want? That's a nat. That's also a nat. But this term has type. This. Is this RFL? Okay, this is RFL. This is definitionally equal. This is just like unwrapping shit. Okay. Now what the hell is the problem? What's the problem? Obviously pack.n. This is like Maybe if this was just n. Well, that's still definitionally equal, of course. But what if this was just like n? Is this still RFL? No. Well, of course not. Maybe I'll ask a question on the zulip. No. Oh, come on. How do I get to the zulip? There you go. Log in. Give me a sec. I think, you know what? I think we did a decent amount. It might be better to stop the stream now. Because we did a decent amount today. Like I explained. So I explained the denoting. Like yeah. I think I'll stop the stream. Cause this is just like busy work. It's not fun for you to watch me do this. Yeah. So okay. I think I'll give it. I'll end it. Right. Okay. So let's do this. Right. So I mean, introduce. I guess I had a good go at introducing it. Okay. And just like continue. Continue furthering the implementation. That's it. I mean, that's just super easy. Yeah, replace expr and lean. Yeah, this is what I wanted to do, but the only way to do this is denotational semantics. Yes, that's the only way to do this is denotational semantics. As functions, you can just pass to opt. This is denotational semantics. Okay, yeah, so I guess like all roads lead to denotational semantics. Yeah, how long do we do this for? No, 2 hours. Can I do like 2.5? Does that work? Hopefully that works. Yeah, that's it, right? That works because it's finished 0 hours ago. Yeah. Okay. Guess goodbye everyone. Thanks for showing up. Yeah, because this is just busy work. This is just like stupid shit I don't want to show you guys. But hopefully I figure out this issue because I wonder how they got it. But yeah. Goodbye everyone. Thanks for the stream.